Hello, ladies and gentlemen. This is Alice from Beijing. I'm so glad to have everyone this Friday again. Yeah, so for iCANX talks, we connect the world and the universe. Since last week, we started this 2021 series. So last week, we have two speakers, Professor Jagdish and Professor Zhang Qing, deliver very nice talk. This week, we will have two young scientists. Yuanmu Yang was from Tsinghua University. Mike Hellcat was from University of Wisconsin Medicine. So both of them are famous young scientists, and both of them are already prepared very nice talk. So we will have a fantastic time this time. I'm sure of that. So now let's welcome our best friends, Jagdish, to introduce all of these young speakers. The first one, Yuanmu. Okay, please.
Okay, thank you very much, Alice. And well, good morning and good afternoon or good evening, wherever you are. And Niman Hao and Wan Shang Hao to my friends in China. And so really, it's a pleasure for me to introduce our rising star, Professor Yuanmu Yang from Tsinghua University. And Professor Yang has done his bachelor's degree in optoelectronics from Tianjin University and then Nankai University. And then he has gone to Vanderbilt University and did his PhD. And afterwards, he worked at Sandia National Laboratory as a postdoctoral fellow, and also later on as a scientist at the Intellectual Ventures, trying to commercialize some of these metasurface technologies which he has been developing. Today, he is going to share with us his exciting work on manipulating light at the sub-wavelength scales and also and related applications. Professor Yang, the floor is yours.
All right. So I hope everyone can see my screen and hear me okay here, right? Okay, so first of all, I'd like to sincerely thank Professor Zhang and Professor Jagdish for this very kind introduction. So my name is Yuanmu, and I joined the Department of Precision Instrument at Tsinghua University about 3 years ago as a tenure track associate professor. Okay. So today, it's really my great honor to take this opportunity to share with you some of our recent work on this topic of how to engineer the light-matter interaction at this sub-wavelength scale and some of the related applications that we have found quite interesting. Okay. So since I found that the topic of today's event is actually the science of light, right? So I just want to give a brief introduction of how I actually get into the field of optics. That was actually during my time as a freshman undergraduate student back in Nankai University. Okay. And this is the first textbook actually I studied. Okay, this is actually a book written by two professors at Peking University. Okay, Professor Zhao Kaihua and Professor Zhong Xihua. Okay. Although I know some of your audience is actually international, right? And you probably don't know this Chinese word, but I guess for most of the introductory optics book, okay, they almost all started with geometrical optics, okay. And the first optical components most of you might have learned is probably just this simple lens, okay, that can be used to focus for collimate light, okay. And the thickness of a typical piece of a glass or polymer lens that's going to be much greater than the wavelengths of light. Later on, as we actually get a better understanding of light and we get into study this topic of wave optics and knowing this diffraction, for example, and interference, okay, we are now able to create probably somewhat a better lens for a more compact lens that's called a Fresnel lens, okay. And later during my graduate school, okay, I got into quite interesting one of the particular subject of optics. And that is a nonlinear optics. Okay, and this is another quite nice book written by Professor Bob Boyd at University of Ottawa. Okay, and throughout this nonlinear optics textbook, most of the time it's been talking about how a strong laser light interacts with the nonlinear crystal, for example, this BBO crystal, that again has a thickness that is much greater than the wavelength light. right? Because you want to have a quite a large length for light matter interaction. Okay? And later, when people realize that you want to actually increase the efficiency of the frequency conversion, okay, they thought about something, a novel type of structure called this nonlinear optical superlattice. This is actually a famous work done by a Chinese scientist, Professor Shilin Zhu, at about more than 20 years ago. Okay, they use this basically this optical quasi-crystal structure. Okay, and by periodically flipping the sign of the optical nonlinear accessibility of the material with a period again on the order of the wavelengths of light. Okay, you are able to basically simultaneously generate a second harmonic and a third harmonic of the light. Okay, with high efficiency. As we see the trend of the evolution of optical components, okay, we'll see that basically as we shrink down the size of the shrink down the characteristic size of each optical element, we're actually seeing better and better performance in terms of, for example, for the focusing light or for getting a better efficiency for nonlinear frequency conversion, right? And up to right now, we are in the year of 2021. Okay, I think as we enter the 21st century, actually there were two major developments that can actually help further advance the field of optics. The first one is that basically with the advancement of nanotechnology. Okay, nowadays we are able to basically manufacture some optical elements with extremely small features that can be really smaller than the wavelengths of light. Okay, and another thing is that with the improvement of the huge improvement of computation power, nowadays we can basically run those full wave simulation of how light and how light interacts with matter at a very small scale. Okay. With that, basically we are able to create effectively a better lens that's basically a sub-wavelength diffractive optics, okay? And many people nowadays are calling it the surface. Okay? This picture actually adopted from the publication back in 2011 by Professor Federico Capasso's group at Harvard. Okay? I believe our next speaker, Professor Mikhail Katz, is also a co-author of this very nice article here. And also in this field of nonlinear optics, okay, we are seeing that if we actually, instead of using this periodic nanostructures, which is on the order of wavelengths of light, okay, if we can actually use some optical thin film, which with a thickness which is much thinner than the wavelength light, there may be something very interesting that can happen, which will lead to new applications in the field of nonlinear optics that we'll discuss in more details later. So, of course, I would like to say that the entire field of sub-wavelength optics is really a huge field. There has been many people working in this area, right? So, for tonight's talk, it's impossible that for me to cover all of them. Okay? But I still want to say that. So, I just for today, I just want to just to give you a few examples that we have been working on over the last few years that we think that may be interesting and maybe you may find it potentially useful. Okay. To get started, I will just first talk about this sub-wavelength diffractive optics. Okay. And many of you might think you don't know that where you can find a piece of diffractive optics in your daily life, right? Then for some of you, maybe you may be using an iPhone. I can tell you that there are actually at least two pieces of diffractive optics just in your iPhone, right? And the first piece is that we have actually a Fresnel lens on the rear camera module here. This is the picture of the iPhone 12 Pro, the newest version. You'll see that actually there are two pieces of Fresnel lens here that is actually to be used for collimating the flashlight. Okay, and in comparison with those bulky glass or polymer lens that's used for imaging purposes here. Okay, you'll see that the Fresnel lens is actually much thinner. Okay, that being said, it can potentially be able to create a much a lens with a much much more compact form factor. Okay, but right now we are only using it for collimation. We're not using it for imaging for now because there are still a lot of problems regarding to this chromatic and achromatic aberration. Okay, we still need to solve maybe with some advanced surface technology out there. And really, this is the second piece of diffractive optical element. That is what I really want to talk to you about tonight. Okay, and that is basically you'll see that on the front end of the iPhone, you'll typically see a big notch here. Many people I know that don't really like. Okay, and inside this notch, actually there is this so-called Face ID module that is used for 3D face unlock. Okay. And inside this 3D face unlock module, and there is a very a critical optical hardware that's called a dot projector. Okay, and I'm going to try to basically explain to you how it actually works. Okay. So inside that dot projector module, there is actually a pixel array here. Okay, that actually generates a laser beam that is collimated by a collimation lens here. Okay. Then the collimated lens is going to go through a diffractive optical element, or shorted for DOE. Okay, what this DOE does is that basically it changes a collimated laser beam into a laser spot array in the far field by the mechanism of multiple diffraction. If we see that this laser spot array is projected onto a flat screen, it's going to be equally spaced here. Okay? However, if you have some 3D object here, for example, this sphere here, you'll see that the laser spot will be distorted, right? Then if you have an infrared camera here to take the picture of this laser spot array here, right? By taking this image and then using some simple algorithm based on this triangulation principle, you will be able to basically to retrieve a 3D image of this thing, okay? This is actually an actual infrared image showing that how face unlock works in the iPhone. You'll see that basically it projects tens of thousands of dots onto your face. Okay, and based on the profile of these laser spots, you will basically give you this face unlock in 3D. Okay, which is much more secure than 2D face unlock using a 2D camera. Right? So in this entire system, one of the key components, as I mentioned earlier, is this diffractive optical element, which is short for DOE, right? And the requirements, there are a few requirements for this DOE, right? First of all, we really want to have a very high diffraction efficiency, right? And next, we really also want to have a very high spot uniformity in terms of the intensity of each dot, right? And last but not least is that we really want this dot projector to give us a very large field of view for this short for FOV, right? That in that way, that basically we'll see a larger range of this thing. Okay? So if you look at the state-of-the-art conventional DOE that's already used right now in your iPhone system, okay, those DOE typically has a characteristic, basically the period much greater than the wavelengths of light. Okay? And most of them are actually a binary phase grid with phase only 0 and pi. Okay, so if you want to design this kind of DOE for laser light projection to a very large field of view, typically can give you quite low efficiency, right? Although you can potentially make a diffractive optical element with a multi-level phase, okay, and that might require this grayscale or a multi-step lithography, which can be not only complicated but also quite expensive. Okay. Here, if we actually create this so-called meta-surface DOE that can have a period less than the wavelengths of light, okay, we may be able to get this quasi-continuous phased manipulation. Then that may be able to give us quite a high efficiency with the large field of view. And also, this entire device can be manufactured with a single-step lithography. It is compatible with this mature fabrication process, such as the stepper lithography or this now imprint. Okay, so this is what we are trying to achieve. Okay, so we are proposing to design this meta-surface-based DOE that can create this 1D laser spot array or this 2D spot array. Okay, and our goal here is that we want to basically achieve a very high diffraction efficiency and a very high spot uniformity. And in the meantime, we really want to achieve an extremely large field of view, let's say above 120 degrees. Okay? And to give you a perspective, for the state-of-the-art DOE used in those commercial electronics, they are typically only have a field of view of maybe somewhere around 60 degrees. Okay, so we are trying to double their field of view. Okay, And in the meantime, we also want this device to be polarization sensitive and the device fabrication to be entirely compatible with the mature fabrication process. And in this case, we are basically designing this silicon nanopillars on top of this fused silicon substrate. Okay, so this is supposedly fully CMOS compatible. Okay. For our device design, basically, essentially we are still trying to design a diffraction grating. Okay. In this case, we are designing a diffraction grating with a total in 1D of 9 diffraction orders from 0 to plus minus 4. Okay. According to this well-known grating equation, if we want to get a full field of view of 120 degrees, that means we need to have a maximum diffraction angle of plus and minus 60 degrees. Okay. If you want our device to operate at the telecom wavelengths of 1.55 micron, that means the size of our, the period of our grating is supposed to be, let's say, roughly 7 micron. Okay. Once the period of the big grating is fixed, okay, then basically what we need to do, we need to design the phase profile within each supercell here, so that we can basically get a uniform distribution of the diffraction intensity across all these different diffraction orders. To do that, basically what we want to do, we want to have the maximum freedom in order to engineer basically the transmission phase of each pixel here. Okay. And to do that, we design this metal surface and a unicell, which is composed this silicon ellipsoid structure. Okay, and by basically sweeping the long and short axis of this silicon resonator, you'll see that we can cover the entire 0 to 2 pi phase range while maintaining a quite high transmittance here. Okay. With that, basically we can get a very flexible control in terms of the design of the phase field. And typically, once we have this, and basically a library of the metal surface antenna design, when people try to design a DOE with a specific far field pattern here, for example, we need to have a nice spot with equal intensity, right? What they do is typically they combine this scalar diffraction series with iterative optimization algorithm. Okay. Basically, you need to design the near field phase profile inside this DOE. Then through some, for example, the Fresnel or Fraunhofer diffraction integral, okay, we can propagate into the far field, then back and forth, then you can get the best phase distribution here. Right? But one of the problem we found in our case is that, first of all, since we are designing a metal surface structure with a period comparable to the wavelengths of light, okay, actually we found that actually the effectiveness of this scalar diffraction theory becomes actually quite questionable. Okay, and also since we are designing a diffraction grating basically with a very large diffraction angle or a very large field of view. Okay, some of the approximation, for example, this paraxial approximation, which is used in the Fraunhofer diffraction integral, actually gets broken. Okay, so this entire measurement becomes actually invalid. Okay, to prove that, actually, we for the first we designed our metal surface simply by this scalar diffraction series, and we found that we can get a very nice and uniform diffraction intensity all the way from minus 60 to plus 60 degrees throughout all these 9 orders, right? But then later we try to verify this result by this vectorial this finite difference time domain simulation. You'll find this result become completely different from what we have predicted from this scalar diffraction series. Okay. With that, basically, we think that we need to find a different measure for this metal surface optimization. Okay. Then we took this approach by combining this vectorial simulation, such as FDTD or this Fourier model measure, in conjunction with some optimization algorithm, for example, this gradient descent algorithm, namely with the interior point measure. Okay, trying to optimize the performance of our metal surface with this figure of merit that is composed of this so-called RMSE and also the EFF. Okay. Basically, this RMSE means root mean square error that determines basically the spot uniformity. The EFF is the term that determines the overall diffraction efficiency. Through our simulation and optimization, we found that basically with our optimized results, maybe it takes about a couple hours for the 1D structure and maybe a couple of days for this 2D structure. Okay, we can get total diffraction efficiency greater than 95% in 1D and greater than 80% in 2D, okay, with an RMSE value of less than 5% in 1D and a little above 20% in 2D. Okay. To give you a perspective, this is really comparable or even better than the state of the art for those conventional DOEs, okay? With only a big difference that we are here doubling this field of view here. Like we're increasing it from 60 to 120 degrees here. So for the device fabrication, it's actually based on some very standard semiconductor fab process using EV lithography and etching process. Okay, and this sample actually is fabricated in collaboration with Professor Xiao Shumin's group at the Harbin Institute of Technology in China. Okay, and you can see this feature really looks pretty nice. Okay, and then to characterize our sample, okay, we build this basically it's a simple Fourier imaging setup, okay, so that we can actually capture how this diffractive light looks like. Okay. And our experiment results show that basically we are now getting a relatively lower efficiency of 55% in 1D and about 59% in 2D. There's also a slightly increased RMSE value. Okay. Although this is not as good as our simulation, but as I have been talking to a few companies working in this area, that they are telling me that it's still quite a decent performance in comparison with some commercial DOE devices. We suspect that one of the main reasons why we are getting relatively worse results compared with simulation is simply because our design right now is still quite intolerant to this fabrication imperfection. Okay, in the future maybe we can further incorporate that in our optimization process. Maybe with that we can get a better result in experiment. So to summarize this very first part, okay, so that we are trying to use meta surface basically to construct sub-wavelength diffractive optical elements to replace those conventional ones for this purpose of structural light projection towards potential applications in 3D sensing. Okay. One of the major advantages here is that it really can have a huge field of view in comparison with those conventional ones. In the meantime, it can maintain a quite high efficiency, high uniformity between polarization sensitive, and its fabrication is relatively straightforward. In the future, we suspect that the outlook part. So right now, our device is operating at the telecom wavelength about 1550 nanometer. Okay. In the future, we may be able to scale the operation to 850 or 940 nanometer, which is the typical VCSEL emission wavelength. As long as we can basically get better control of the fabrication, so we need to make the resonator slightly smaller in the future. And also, one thing I want to mention is that at the near infrared wavelengths of 850 and 940, actually, amorphous silicon is still quite transparent. Right? Still, that means basically by changing it into this changing the wavelengths, we won't actually suffer a penalty in terms of the diffraction efficiency. Okay. So we are seeing that it might have a potential application in consumer electronics, probably not limited to iPhone, but also, for example, in your Microsoft Connect, those gaming consoles. Okay, anything that demands depth sensing, depth perception over a large field of view. Okay, that's the first part. Now let's move to the second part. Is that the imaging through. I'm going to talk about how we can use this meta surface polarization imaging. So to begin, I want to give you some perspective. So why we want to do this? The motivation here is that we want to basically try to image through this turbine media, for example, through this haze or sandstorm or snow or some dirty water, right? For example, it can have a lot of applications for, let's say, remote sensing or autonomous cars here, right? So of course, to do this, okay, one approach is basically to use a software-based approach. For example, using some simple algorithm, for example, like histogram equalization, right? It has some limited effectiveness. And there are some new methods, for example, using a deep learning to basically to get a better image contrast. But that might require a prior knowledge of the thing, or actually also requires some computation power resources out there, right? So back in 2003, actually, there's a group by Professor Shishner's group in Technion in Israel. Okay. They proposed a method to do this polarization-based imaging through haze. Okay. Without going into much details of those maths, okay, I only briefly explain how this thing works. Okay, so if you have a camera or your eyes right over here, and you want to see this faraway house right here, okay, what your eye actually is going to receive this other than this direct transmission of the object light. Okay, You're also going to see some scatter light from some scattering particle in the air. Okay? But there is a major difference between the light coming out from the object and from the scattering particle here, that the object radiance is typically unpolarized. And in the meantime, the scattered light is typically partially polarized. Okay, so that if you put a polarization filter right in front of your camera, and by taking two images with orthogonal polarization, by applying some polarization and differentiation algorithm, you can potentially try to subtract this air light and only get this direct transmission light. Okay, by doing that, and they have shown that it's possible that you can get an image with a much improved image contrast just through this polarization imaging. But one of the limitation at that time is on the hardware. You'll see that most of the time when they do in the old-fashioned way of doing this, basically they need to manually rotate the polarizer in front of the camera, which is obviously not good for application, right? Although a few years ago, like Sony has released its commercial polarization camera that's called the PolarSense. Okay, how it works is basically they are able to place a bunch of micro polarizer right in front of their camera sensors here. Okay, and because they have this polarization filter here, by combining, for example, 4 pixels and forming a super pixel, you are able to take basically a polarization image here. Right? But one of the limitations of this polarization camera is that, first of all, by using this polarization filter, that basically means if you are taking an image of an unpolarized thing, that means you at least will reject 50% of the light. Okay? And also, actually, to build this polarization camera, you need to redesign your camera sensor. That can be actually quite expensive and quite difficult. Okay? So a few years ago, a few research group, one by Professor Andrew Farran's group, okay, at Caltech, and also later by Professor Capasso's group at Harvard, they proposed we can use this concept of a meta lens for polarization imaging. Okay. The key concept here is that as we see those conventional Fresnel lens, they are typically like polarization insensitive. Okay, but for this meta lens, we can design the meta lens antenna unit cell such that we can design to be a polarization sensitive. For example, by using this rectangular shape antenna. Okay, so they can get we can impose a different phase profile of light with different polarization. Okay, so that, for example, we can design a lens that can focus both this X polarized and Y polarized light onto the same focal plane, but with the laterally shifted focal point. Right. The key advantage of this is that basically, in this case, we can do this single shot imaging for both polarization, right? And also, unlike the polarization filter approach, in this case, we are essentially doing this polarization splitting, right? So our focusing efficiency can be, in principle, greater than 50%, overall higher efficiency, right? And in this case, we are basically just changing the imaging optics, and there's no need to redesign the camera sensor. Okay? So in this particular work, we really are inspired by this a very similar design, like the one done by the Andrew Farran's group. And the work we are actually trying to do is actually trying to demonstrate how we can actually use this meta lens for polarization imaging through milky water. So, for example, if we have an LED light with a center wavelength at about 800 nanometers, okay, we shine it onto, for example, this toy of a shark here. Okay, and if this toy is placed in a tank filled of diluted milk, okay, and we put our imaging camera somewhere outside, okay, so we want to really see through this milky water, and if you want to see, we use the polarization imaging setup, can we get a more clearer image of the shark. Okay. This is actually our actual experimental setup. You'll see that the LED comes onto the light source comes onto this target meta lens, and CCD camera is here. Okay. So to actually do this, we fabricated a meta lens with a quite large diameter of about 3 millimeters with the SEM picture showing here. This fabrication is actually done in collaboration with Professor Chen Zhang at Huazhong University of Science and Technology in China. Okay. So let's see our experimental imaging result. In this case, we are actually tried both 2 different samples. One is the grayscale image of the shark. Another is the black and white image of the fish, or which I don't know what kind it is. Right? Okay. So with this, you will see that basically, if we actually take a regular image without doing this polarization differentiation analysis, okay, we'll see that basically all these images in different milk volume fraction, it can be quite, you can see quite blurry here, right? After applying this polarization analysis, you'll find that if we judge it using this so-called layer of enhancement for this value of EME, okay, you'll see basically the image contrast can be improved sometimes even by more than 10 times. Okay. For example, in this picture here, you'll see that maybe here you won't actually see anything right here, but with this polarization analysis, you can sort of see this shark here. Also, as a byproduct, we found that by applying this polarization imaging technique, we can also be able to actually estimate the depth of the object. Okay, and the underlying principle is that the total transmittance of this object radius is actually going to be distance dependent. Okay, with this inside this equation, we'll see this T actually means the total transmittance of the object radius, and the term beta here is the effective extinction coefficient of the Milky Water. Okay, as from this polarization analysis, we are actually able to basically retrieve the value of T, and if you can actually know or fit this extinction coefficient of this Milky Water, we are actually be able to render a depth map of the thing. Okay. So in the experiment, we find that we can basically put two objects with at different Z position. Okay, by doing this polarization analysis, we are actually be able to generate or at least estimate the depth of this each object. Okay, so to summarize this part, basically we need this subwavelength, like the so-called meta lens with this subwavelength meta antennas for this polarization imaging. Okay, with these advantages that we can do this real-time polarization imaging for subnode polarization. Okay, with a relatively high focusing efficiency, as we actually measure the diffraction efficiency. Focusing efficiency is greater than 50%. And also compared to other bulky lens, it can have a low size, weight, and power. Okay, and for application, we have kind of give a proof of concept demonstration that we can use it for imaging through turbine media, and also to achieve this depth estimation. And we can envision that we have a potential application, for example, in remote sensing, and in some other people right now are very interested, for example, in ocean optics. With that, I'm going to completely switch gears and talk about this like this subwavelength nonlinear optics. Okay. So first, I still want to give you a motivation of why we want to work on optics. Okay. So this is probably the electromagnetic spectrum. Many of you are quite familiar with. In the visible or in the near infrared, we have a lot of options for lasers. Okay. But if you actually go to longer wavelengths, let's say into this terahertz domain, or into shorter wavelengths, into the UV or in the X-ray range, okay, you'll find actually we have quite limited option for this direct coherent source operating in the UV or in the terahertz spectral range. Actually, in last week's iCANX talk by Professor Jagdish, he has also mentioned that you can use this ultra-fast dynamics in those semiconductor nanowires to actually to use the photoconductive effect to create some broadband terahertz source. Okay. There is another way basically to create this UV and the terahertz source, that is through this principle of nonlinear optics. Okay. For example, if you have a TISAF laser with a wavelength at 800 nanometer, then by using this principle of second or third harmonic generation, okay, you can basically upconvert your photon energy and basically get a UV light, okay, using a nonlinear crystal, for example, this BBO, okay. And if you want to get a broadband terahertz source, then you can use this difference frequency generation process, okay. So if you have two infrared laser beam with slightly different angular frequency, okay, through this DFG process, you may be able to get a light signal with a relatively low photon energy in the terahertz domain. Okay. For example, if you shine a femtosecond laser onto this nonlinear zinc telluride crystal, okay, through this so-called intra-pulse difference frequency generation process, you may be able to get a broadband terahertz emission. But there are a couple of problems with conventional nonlinear crystals. The first one is as I mentioned in the beginning, called as phase matching. Okay. So in order to get a very efficient frequency conversion, okay, other than to satisfy this energy matching condition, okay, you also need to satisfy this phase matching condition. Okay. In terms of getting an efficient terahertz generation, okay, actually it requires basically your nonlinear crystal to have identical refractive index in the near IR and also in the terahertz. Okay. As an example, one of the most popular nonlinear crystals, such as lithium niobate, okay, because lithium niobate actually has the optical phonon resonance somewhere in the mid IR. Okay. So you'll see that refractive index of lithium niobate is drastically different in near IR and in the terahertz. Okay. You'll see that in the near IR it had a refractive index of 2.3, and in the terahertz its refractive index is 5. Okay. So many of the conventional methods for phase matching, such as the Cauchy phase matching or birefringent phase matching, they probably don't work as well for this purpose. Okay. And another problem for this nonlinear crystal is this material absorption. Okay. Especially if you want to, for example, generate light in the UV domain. Okay. So even for most of the UV nonlinear crystals like BPO or QBBF, okay, they all have an absorption edge somewhere greater than 160 nanometers. Okay. So if you want to get a coherent light source with the wavelength shorter than 160 nanometers, okay, they probably won't work anymore. Okay. And if you want to generate light in the terahertz domain, okay, and many of the nonlinear crystals, such as the one often used as zinc telluride, okay, you can have this phonon absorption, for example, at 5 terahertz. Okay. So if you really want the broadband terahertz generation, you'll find that basically there will be a few spectral gaps in your entire light source, which is not ideal. Okay. So in order to address these two problems, okay, you'll see that basically we will see that basically most of the time our nonlinear crystal have a thickness much greater than the wavelength of light, okay, on the order of, let's say, 1 millimeter or 1 centimeter. Okay. What if we create this nonlinear thin film with a thickness that is smaller than the wavelength of light? Okay. Let's say about 10 nanometers. Okay. Upon first look, you might see that it might solve this is like a one stone, two birds. Okay, you'll solve both of these two problems here. Okay. Since if our thickness of the material is going to be thinner than the coherent length for this harmonic generation, then we don't need to worry about the phase matching anymore. Okay. And also the thickness, if it's smaller than this absorption length of the material at this harmonic wavelength, then this material absorption also becomes less of an issue. But then upon a more careful look, you'll find that there is a big problem here, right? So if for a nonlinear crystal, the light matter interaction length is 1 millimeter. It's 5 orders of magnitude longer than a thin film of only 10 nanometers. Okay. So the big outstanding issue here is how can we possibly get this strong light matter interaction inside this ultra thin or this sub-wavelength thin film in order to get efficient harmonic generation. So our solution here is to use this so-called epsilon near zero or ENV material to construct this nonlinear thin film. Okay. And here, by saying epsilon, we mean the permittivity of the material, which is, as you see, the refractive index of material is basically the square root of epsilon. Okay. So let's see what will happen inside a material made of, inside a thin film made of this ENV material. Okay. Let's assume that we have a p-polarized light with oblique incidence from air into this material with permittivity equal to 0. Okay. So according to this boundary condition that can be derived from this Maxwell equation, we will know that across the interface of two materials, okay, we'll see basically the normal component of the displacement field are going to be continuous across this interface. And the displacement field can be written as the permittivity epsilon times the electric field E, right? And in air, if we have a finite epsilon 1 and E1 and E2 goes to 0, does that mean basically the epsilon 2 goes to 0? Does that mean the E2, basically the electric field inside this ENV material is going to approach infinity, right? That means basically we'll get a huge enhancement of the light matter interaction that can potentially boost our nonlinear frequency conversion process, right? Of course, here anything that goes to infinity seems quite questionable, right? in any realistic material, when its permittivity goes to a real part of its permittivity goes to zero, oftentimes it's also accompanied by some finite part of the imaginary permittivity, right? So depending on the magnitude of the imaginary part of permittivity, so you can still get a field enhancement maybe on the order of a few tens or a few hundreds. Okay. So this effect actually is not that new. Okay, a few years ago, one of my friend, Professor Liu Wei from the National Defense University of Technology of China, okay, he sent me an email quoting the biography of famous physicist Landau. Okay, it was found that one of the Landau's student Vito, okay, he actually identified this inflation of the electric field inside this ENV medium even back in 1939. Okay, and when he mentioned this to Landau, okay, Landau only just gave him a very simple response. Okay? He said only 2 words. Okay? This is of course. Okay, that basically means this is something really simple and intuitive. Okay? So there's nothing fancy here. Okay. Of course, the problem becomes like how can you actually create a material with this epsilon near zero response? Okay. One way to do this is basically to use this very simple effective media approach. Okay, basically by stacking different materials with both either a positive or refractive or a negative permittivity here. Okay, this is a very nice experimental work that was done in collaboration between Professor Negro and Gelta and Professor Albert Pullman. And later, people also found that you can actually create this photonic crystal structure with something called something like a Dirac cone dispersion. This can give you both a material permittivity and permeability mu simultaneously crossing zero. And this concept was originally proposed by Professor C.T. Chan's group in Hong Kong University of Science and Technology. Okay. Actually, this was one of my first project during my graduate school. Okay. We were probably one of the first to demonstrate optical nanomaterials with both permittivity and permeability crossing zero in the optical frequency. But today, what I want to talk to you is that really that this kind of ENV material does not need to be created from those artificial structures. Actually, it widely exists in nature. If you recall what you may have learned in solid-state physics, you'll see that the permittivity of a typical metal that can be described by this so-called Drude model. Okay, in the Drude model, basically it determines what the permittivity of a metal as a function of the angular frequency of light looks like, right? So here there are 2 important parameters. One is the plasma frequency, omega p of the material, and the gamma, I mean the plasma damping. Okay, if for now we ignore this plasma damping term here, you'll find that when the angular frequency of the light exactly equals the plasma frequency of the material, you'll find that 1 minus 1 equal to 0, right? Then at the plasma frequency of the material, you'll see that the real part of the permittivity will cross 0. Of course, due to the finite plasma damping, we'll still have some finite imaginary permittivity in the material. Okay. To give you an example, okay, one of the very commonly seen in the material is this ITO, which is basically used for your transparent conducting electrode, also in your iPhone. Okay. So ITO basically is a conductive metal oxide that, with its permittivity, also can be governed by this Drude model. Okay. You'll see that for ITO, its permittivity will cross 0 somewhere in the near infrared range. Okay. And actually, since if you look at the equation governing the plasma frequency of the material, you'll see that there are many materials with different electron density that actually, depending on the exact electron density here, okay, we have a wide range of semiconductor and doped metal oxide or metal nitride or double metal. Okay, we all can have an ENV response. Okay, spanning from all the way from this terrace to this UV range. Okay, and there are other possibilities. For example, you can basically have those polar dielectrics such as silicon carbide or hexagonal nitride, which may have also an ENV response near its LO phonon frequency. Okay. So over the past few years, there has been many work, okay, trying to use this enhanced light-matter interaction in this natural thin film material made of this evenly material, okay, trying to enhance some nonlinear optical process. For example, second harmonic generation, third harmonic generation, for this. For example, this work we have done also during my postdoc at Sandia. We did an ultra-fast amplitude and polarization switch, okay, using this ENE material to construct this perfect absorber structure. Okay. If you want to get a better understanding of this entire field, in recent years has been a number of very nice review papers coming out. For example, you can read this one by Dr. Ora Risha that is published on Nature Review Materials 2 years ago. Okay. But one of the questions that we have been asking is that although we know that this ENE material can be used to enhance the efficiency of second harmonic or third harmonic generation, right? But we also know that for all those bulk nonlinear crystals, nowadays they can achieve a harmonic generation efficiency maybe 50% or even higher, right? Although this ENE material can be used to enhance the harmonic generation efficiency, the number is still on the order of 10 to the minus 5 or 10 to the minus 6. Okay. So with such a low generation efficiency, how can it possible to be useful? Okay. So our mindset is that we really have to find some unique applications that probably those nonlinear crystals are not doing so well, so that we can catch up with our subwavelength thin films. Okay. And the first of such application we find is this something called the high harmonic generation. Okay, so for high harmonic generation, what happens is essentially that we have n photon, n numbers of photon with angular frequency of omega. Okay, combines to form one photon with a total energy of n omega. Okay, you might see this is a quite weak nonlinear optical process, right? It can actually have a lot of applications. For example, nowadays, in order to generate this isolated autosecond pulse with extremely short pulse duration, okay, predominantly it has been done using this process of high harmonic generation. So also, if you actually, by using this high harmonic generation process, you can create photons with very high energy all the way into the EUV or soft X-rays, okay. You can be able to actually do a lot of very nice spectroscopy work or photospectroscopy work, okay, just using this method, okay. But one of the things that, to our surprise, is that traditionally this high harmonic generation has mostly been done in inert gas. Okay, one of the main reasons for that is actually all those inert gases might have quite a high damage threshold. Okay, so that you can use a very strong laser to pump it and to generate harmonic light even up to hundreds or even thousands of orders. Okay. But one of the problems with gas-phase high harmonic generation is that the setups is going to be quite cumbersome. Okay. It was until almost 10 years ago, okay, one of our later collaborator, Professor Shenbu Jamir's group at SLAC in the US, okay, for the first time has demonstrated that the high harmonic generation in a solid state zinc oxide crystal, okay. By doing this solid phase high harmonic generation, one of the main advantage here is that you obviously can have a much more compact setup, okay. But there are two major problems here. One of them is for the solid target, they typically have a quite low damage threshold. Okay. And the second thing is that since we're oftentimes interested in high harmonic generation all the way to a very high photon energy to the extreme UV or let's say X-ray range, okay, all these nonlinear crystals, they may have a quite large absorption because photon energy is already above the material band gap. Okay. Because of that, people have been thinking about can we actually increase the high harmonic generation at the surface of the material, okay? For example, by using these plasmonic nanostructures. But later they found that one of the biggest issue of using this plasmonic nano antenna is that this plasmonic nanostructure, they can really have very, very low laser damage threshold, okay, up to tens of gigawatt per centimeter squared peak intensity, then that will get burned or just melted, okay? So that's where we found that we may have an opportunity basically to do this high harmonic generation or doing this strong field laser physics experiment using this thin film of epsilon 00 material. And the particular END material we use is called this indium doped cadmium oxide. Okay. So cadmium oxide is the material that is similar to ITO. It's also a conductive metal oxide, but it has a higher electromobility, meaning that when at its EME wavelength, it has a relatively a low imaginary part of permittivity that can give us a much higher field enhancement than ITO. Okay? And this sample is grown for us by our collaborator, Professor Zhongpao Maria's group, right now at Penn State University. Okay? And on our sample, we further added a layer of gold in order to further enhance light matter interaction inside this cadmium oxide layer. Okay? For the experiment, we are going to shine a femtosecond laser, okay, at the ENV wavelength of CDO, right? And we are trying to measure the high harmonic generation on the reflection side. Okay? Because of this epsilon zero effect, okay, we can expect from this transfer matrix calculation, you can indeed get a large field enhancement inside this ENV layer. Okay? And another important thing is that since our ENV thin film, this kind of thin film, only has a thickness of 75 nanometer, it's actually comparable to the absorption length of the material in this UV range. Okay? So we can still get quite an efficient extraction of this harmonic signal this way. Okay? So in the experiment, first we use S-polarized light to shine on our sample. In this case, we are not exciting this ENV resonance. Then we are only get the third harmonic generation, right? Then we change our pump polarization to the P-polarized light. We are seeing this high harmonic generation all the way from the third to the nice order. Okay? And also we see this process actually becomes the non-perturbative scaling, meaning that, for example, our third and fifth harmonic generation doesn't follow the rule of I cube and I to the fifth. Okay? What we feel like the biggest advantage of this device is that unlike for typical gas or solid phase high harmonic generation, it often requires a peak pump intensity on the order of terawatt per centimeter squares. In this case, due to the enhancement of the ENV effect, we only require the order of pump intensity on the order of 10 gigawatt per centimeter squares in order to get this nice harmonic generation here, which is 2 orders of magnitude improvement. Okay. And also further found the quite peculiar physical phenomenon that in our high harmonic spectrum we get this very interesting spectral shift and broadening, meaning that in our fifth harmonic signal, okay, we are seeing basically a redshifted harmonic peak as well as a broadened harmonic peak in comparison with a signal which is non-resonant. Okay. We are explaining this broadening of this shift of the high harmonic signal using this some hot electron dynamics in CDO as well as by building this time varying epsilon near zero cavity. Okay. One of the major potential like application of having this broadened spectral peak in terms of this harmonic signal is that we can use this phenomenon to try to shrink the pulse duration of this harmonic signal in the time domain, such that we can actually get a very short pulse towards, for example, to generate isolated attosecond pulse. Okay. So to summarize this part, we did high harmonic generation using this subwavelength ENV field with very low pump threshold, and the sample has a quite high damage threshold, and also see this quite particular feature of this high harmonic spectral shift and broadening. Okay. And last, we want to see that the outlook. So we want to use this structure maybe to create this vacuum UV source with high photon flux, because in this case, we actually can use a pump laser with very high radiation rate. And also we can potentially use this unique spectral shift and broadening to promote the generation of isolated attosecond pulse. Okay. The last, I want to show you how we can also use the ENV effect to try to create terahertz radiation. Okay. The terahertz radiation has a frequency somewhere in the range of 0.1 to 10 terahertz with wavelengths about 30 micron to about 3 millimeter. It can actually have quite a lot of application, for example, for spectroscopy, because it has a fingerprint for many drugs and explosives. Okay, and also it can be used for imaging because you can see through many things, such as this newspaper. Okay, and it's reflective for metal. Okay. So the conventional way, one of the conventional way to generate the broadband terahertz source is using this nonlinear crystal, such as this zinc telluride. But it has this limitation of a very limited bandwidth, typically smaller than 3 terahertz. That is limited by this phase mismatch, as well as this absorption of this nonlinear crystal. Okay, and also this nonlinear crystal, they are not cheap. Okay, typically they're greater than $1,000 US. Okay. So what we are proposing actually is to use this nonlinear epsilon near zero thin films to create a terms light. Okay, and by meaning this ENV thin film is simply a ENV an ITO glass that you can buy basically off the shelf with very low cost. Okay, one of the advantage of this ENV material for terrace generation is that because it's really thin, so theoretically it really can give you an unlimited terrace bandwidth. Okay. So in the experiment, what we are trying to do is basically try to use the IR laser beam to pump this ITO film. By using this surface difference frequency generation process, we are trying to see if we can generate any terrace pulse either in this transmission or in the reflection side. Okay. So first, we actually bought a commercially available ITO film with a thickness of 19 nanometer, and we characterized its a linear optical performance. I found that indeed it can have a real power of permittivity crossing a zero at about 1400 nanometer with a corresponding large field enhancement. Okay. Then later, in collaboration with Professor Han Jiaguang's group at Tianjin University in China, okay, we built this terrace time domain emission spectroscopy setup to see if we can actually generate a terrace wave from ITO. Okay. So for the experimental setup, first of all, we have a TISAF amplifier that pumps a optical parametric amplifier. Okay. Then we can shine the laser either in transmission or in reflection side onto our ITO glass sample. Okay. So if we can later generate some terrace wave, then we can use a separate probe beam actually and use something called optical sampling setup. Okay. By scanning this delay stage, okay, we can actually generate a time domain waveform of the terahertz signal. Okay. So this is our experimental result. You see, for the time domain signal, we see that both in transmission and in reflection configuration, we are seeing basically this very narrow pulse with the pulse duration less than 1 picosecond. That basically means if we actually do a Fourier transform, okay, you'll see a broadband terahertz signal with spanning a wavelength of a couple of terahertz. Okay. In our current experiment, we are seeing a terahertz bandwidth barely above 3 terahertz. Okay. Right now, we think it's still, of course, not unlimited. Right now, we think our bandwidth limitation is there are two of them. Okay. The first one is that our laser pump laser has a pulse duration of roughly 100 femtosecond. Okay. Another thing is right now for our electro-optical sampling setup, okay, we are still using a zinc telluride crystal that is a mismatch at a frequency greater than 3 hertz. Okay. In the future, we expect that there's still no fundamental limitation in terms of the bandwidth of our device. The last thing I want to say that people most are interested in how efficient this is. Okay. So we did a direct comparison of the terrace signal generated from the 19 nanometer ITO film and compare it with a zinc telluride crystal with 1 millimeter thickness, which is much thicker than this. Okay, and we found that this terahertz field amplitude is actually only roughly 1/30 of that of zinc telluride crystal with a much larger thickness. Okay, that is actually quite, although not as good, but it's quite an encouraging signal for us, right? So to summarize this last part, okay, so what we have been doing is basically this, we have shown that we can actually generate a broadband terrace pulse with this very simple sub-wavelength ENV film, essentially made out of this commercially available ITO glass, which can give you a quite large broadband width and quite low cost and some sort of kind of a moderate efficiency, right? For the outlook, we can still expect that if we can actually use ENV material, probably with a lower loss and a larger field enhancement, that may be able to help us further enhance the terahertz generation efficiency to be maybe even comparable with those bulky zinc oxide crystal. Okay. Also, although right now we are using the optical parametric amplifier system to pump the ITO, okay, that can be quite expensive. But the pump wavelengths can be scaled, for example, to 1550 nanometers. So the sample can be pumped by a typical fiber laser. Okay, that can be simply done by changing the doping of the ITO such that we can move its ENV wavelengths, let's say, to this telecom fiber. Okay. So to summarize my talk today, okay, I hope through this last hour, okay, I kind of maybe convince you that by going into this subwavelength scale, okay, we can create some very interesting optical components for application in diffractive optics and in nonlinear optics that cannot be done really with some larger scale optical component. Okay. So to conclude my talk, I want to just finish just by probably one of the very famous saying by Richard Feynman back in 1959. Okay, that is there is plenty of room at the bottom. Okay, you see that there's really we have 16 years has gone by. Okay, I hope to see that probably there's really still a lot of room at the bottom, so we can keep exploring and find some more exciting applications out there. Okay. So in the end, I would like to acknowledge all my postdoc and students, and including undergraduate and graduate students here. Okay, really, one of the biggest advantages for working at Tsinghua is really we can have a lot of really fantastic people around us, and to help to help on all this project, right? And also, I would like to thank all of my collaborators. You can see all of them, both in the U.S. and also in China. Without them, none of this can be possible. In the end, I just we also thank all my funding agencies, and also I just want to give a short advertisement that we are still actively looking for students and postdoc, and if you're interested, just shoot me an email. Okay, and I'm happy to answer any questions. Thank you all. Yeah.
Thank you, Professor Yang, for a very impressive talk, and so really impressive results and also beautiful talk, and then you've done a great job. And so really, there are many questions from the community on your exciting talk. And the first question is, what are the challenges in commercializing meta surfaces?
Well, I guess, first of all, that's a very good question and a very important question, I think. I think to us, and I feel like for commercializing meta surfaces, one of the biggest hurdles that we need to cross, personally, I feel is that we still need to solve the problem of the large-scale manufacturing of this device. Especially right now, for passive device, for example, we can use some techniques such as nano imprinting, but for the active device, we really have to think about how can we maybe develop a process that's compatible with this entire CMOS foundry process, right? And also for the on the design end, many people are actually excited to see can we actually use, for example, meta lens trying to replace the bulky glass lens in your iPhone, for example, right? So I think there are still many scientific challenges out there. So, for example, how to actually create to correct this chromatic aberrations of it. So, but I think there is still a very exciting field. Especially, I won't expect that all these meta-optical components can replace everything, but still for certain applications, we might find it useful. That's really enough. That's my personal take on this. Yeah. Thank you.
Okay, thank you very much. And the next question is, what are the critical parameters which influence the efficiency of meta surface DOE?
Well, I guess this is another very interesting question. Okay, I guess, well, there are a lot of things that can be said here. But one of the things I can think about right now is that you really have to want to have a lot of enough space. For example, we have to we want to have like the entire control of the face all the way from 0 to 2 pi. And it's important to have your material is not lossy, right? That's another key. And sometimes what we have seen before is that, for example, if you want to design a meta lens with a very high numerical aperture, or to design a diffractive optical element with a large diffraction angle, it's important to know that some of the concept developed for inside this scalar diffraction theory actually doesn't work. Okay? You are going to see a lot of coupling between all those antennas, so that there are a lot of optimization work you need to do in order to further optimize the efficiency of your device. Yeah.
Okay, thank you very much. And the next question is, in designing meta lens, you mentioned that the size of one diffraction unit is fixed at about 1 micron. But I noticed that in the figures, there are multiple diffraction units. Why do you need so many units? How many units it is needed to design a satisfactory meta lens?
Okay, that's another important question. Okay, so I guess you can still see my screen or not? Hello, can you still see my screen here? I don't know. Probably not, right?
No, we can't see it yet.
Oh, okay. So
You
basically,
can just tell people. Yeah.
Okay. So that's something that I was trying to explain with this supercell and unicell. Okay. So what we are having here really is just a diffraction gradient that we need those multiple diffraction orders. That's why we actually need a supercell with a period of like 7 microns. With a 7 micron period, that's why we are having these multiple diffraction orders, because we need to have a laser spot array, not just one spot. And within that supercell with a period of 7 micron, we have like many unicells of meta surface or meta antennas. The purpose of those meta surface antenna, that's to basically give us a full coverage of all kinds of possible phase. Right? But still, we're making a big piece of grating with a period that is larger than the wavelength of light. Yeah.
Okay, thank you very much. The next question is, I noticed that many near-field light manipulation methods, for example, surface plasmonic resonance, have a relatively narrow optical bandwidth. For a particular meta lens, what is a typical bandwidth? Is this comparable with conventional lens? Or can it span, for example, throughout the visible light bandwidth so that it could be possible to use in future cameras?
Yeah, that's another very important question in this entire meta optics world, right? So one of the major problems with all this meta lens is that still this chromatic aberration or this bandwidth issue is actually, I don't think it's solved yet. Okay, there has been a number of papers trying to address this issue, for example, by Professor Akimaso's group and by Professor Chai Linping and Professor Zhu Shiling's group in China. Okay. But still, I don't think this problem is fully addressed. When people try to say that they solve this problem of doing this achromatic meta lens, okay, there is a penalty here that comes that for all those achromatic meta lenses, actually you can only design for a very small numerical aperture or a very small aperture size, right? So the bandwidth issue is I don't think it's solved yet. Okay, but I would still want to argue that there are actually many applications. Actually, you probably don't need a broad bandwidth. Okay, for example, just the one I showed that if you want to use it for this laser spot projection, the structural projection, actually it's designed to be used, for example, with a VCSEL. Okay, that's a narrowband illumination that can still work quite well. Okay. Yeah.
Okay, thank you very much. The next question is, the artificial structure presented as ENZ materials is a periodic structure, look very much like the normally used quasi-phase matching structures in nonlinear optics. How is ENZ materials better?
Well, that's something that may be confusing, I guess, and that's a very good question again. And the one I mentioned that the artificial ENA material made of this positive and negative permittivity material, actually they're based on this so-called effective media approach. And there is a precondition for that. And that is basically the period of each layer. Actually, they are required to be much smaller than the wavelengths of light. Okay. And that's different from this quasi-phase matched crystal, which has the period that is underwater with the wavelength of light. Okay. So, I mean, there may be some interesting applications using this effective media material for nonlinear optics, but I guess it's remains to be looked into more. Yeah.
Yep. Okay, thank you. For the ENZ enhancement of harmonic generation, so you mentioned that HHG, but why do we use HHG? Can't we work just being done through combining second harmonic generation, third harmonic generation? For example, fourth harmonic generation is just 2 times the second harmonic generation, and the efficiency would be much higher.
Well, that's another important question. Okay, so right now we are getting this harmonic signal. For example, the third harmonic, fifth harmonic, and let's say the ninth harmonic. But right now, we don't know it is done through this Chi3, Chi5, or Chi7 term, or is it done by this cascading nonlinear process, right? That's something we don't know yet. But I guess what matters in the end is that still can we actually get this very high order harmonics, right? And yeah, that's something. I mean, it's very hard to distinguish. Yes.
Okay, thank you. The last question. For ENZ enhancement of harmonic generation, a real epsilon goes to zero, the losses typically go up with heating. Is the optimal real part of the epsilon is equal to zero or not quite? Is it possible to calculate theoretical bounds on what can be achieved in terms of harmonic generation efficiency, given the trade-off between how close real part of epsilon is to zero and losses?
Okay, that's another good question. Okay, what we have found throughout our modeling about this nonlinear optical of ENV material, nonlinear optical properties of ENV material, that we actually found that although there is always a loss associated with this ENV point, right? But still, the largest field enhancement still occurs uh, almost for at least very close to this ENV frequency. But one of the interesting things we indeed found is that sometimes the maximum harmonic generation efficiency may not exactly occur right at the static ENV frequency of the material. And that can be explained by some of the more, I would say, complicated hot electron dynamics in there, and also some very interesting non-local effect here. I didn't really spend time to explain that in detail. And I guess if any of you is interested, later on we can you can feel free to shoot me an email, and I can try to explain in really more details about that. Yeah.
Okay, I think we'll close the Q&A session at this point because I think we've covered quite a bit and also exceeded allocated time. And I would like to take this opportunity to thank you for giving an excellent talk and also sharing your experiences in this field and also answering all our questions and questions for our audience. Thank you very much.
Right. Yeah. Thank you, Professor Jagdish, and thank you all for listening.
Thank you. So now we'll go for the panel discussion. And we also have got, along with Professor Yang, and then we've got Professor Mikhail Katz from the University of Wisconsin-Madison. And then really great to have two young scientists with us today. And then we'll be really learning from them about how they chose their careers and then how they've set up their labs and then what type of advice they can give to the students. With that, maybe Alice, you want to say anything, or
Oh,
we can
yes. I think
please
the
go ahead.
panel discussion will be very interesting because I do, yeah, want to ask two of them questions. At this time, we have this really young scientists, and both of them do so well. Another thing is that they looks very handsome, right? They are not only smart, but also very handsome. And they should have a lot of choice, even can be movie star. But why would they choose to go to academic to be a scientist, a professor? Such a tough job. Okay, who goes the first?
I guess Mikhail can go first, I guess.
Sure. Well, thank you so much to Professor Alice Jung for inviting me here. It's really an honor, and it's a pleasure to see Yuanmu's talk as well. I think I don't have the same confidence that Alice does in my ability to go into to Hollywood or any other such activities. But I do appreciate her evaluation. Nevertheless, why go into this career? I think there are a couple elements here. One is that I really believe that for kind of intellectual satisfaction and for happiness, the environment is very important. And so, in other words, you want to surround yourself with smart, thoughtful, hardworking people, or at least I want to surround myself with
Good.
smart, hardworking, and thoughtful people And being at a university, being at a major research university like the University of Wisconsin-Madison was really kind of a wonderful place to be for my career. I think also the fact that there's kind of a renewable resource, which is students who are young and energetic. I think it's really it's really kind of great and energizing. The other reason, and as compared to, for example, other large institutions which are intellectually stimulating, like large companies or national labs or things like that, I'm really excited to pursue kind of intellectually challenging research that doesn't necessarily have an obvious goal or an obvious application attached to it, at least not one that's immediately obvious. And academia really gives you the opportunity to go down these kind of rabbit holes and to explore compelling experiments and compelling theoretical arguments, even if the final application is not quite yet in sight. And I just find that very intellectually stimulating. So I think
How
those are
nice
my.
for you say that. For the people surrounding us, smart and hardworking. Actually, get me ideas on iCANX every week. Every Friday, we met all the people like this. Professor Jack Dish now is already midnight. And Professor Paul was in the early morning, 4 o'clock every week, for to see the sunrise on the LA, right? That's exactly the hardworking people, the smart people everywhere. Yeah. Okay,
This is why
Yuanmu,
we're
how
here. So
about you?
thank you, Alice, for bringing us together.
Yuanmu.
All right, so yeah, thanks, Alice. And I guess for many of us graduating from a PhD program, that we're facing the problem whether to go to the industry or stay in the academia, right? For me, myself, actually, I don't know. Okay, so I didn't know when I was graduating. So actually, I took the approach that I give it a try. So I spent 2 years as a postdoc at Sandia. Then after that, I was actually really get tired about academia, right? So I don't like keep publishing paper anymore. So I want to make something actually useful, not like Mikhail, I guess. So at that time, I actually got a quite nice opportunity to join a startup trying to commercialize this meta surface technology for just application LiDAR for automotive autonomous cars. Okay, and one of my friend Gleb Axelrod at that time approached me, and I was actually was able to basically to apply some of the knowledge and learned or research during my PhD study and try to make something actually useful. Okay. And during that, about a year in like a startup company, actually, I guess myself, I actually I learned a lot from that. Okay, actually to how to develop a concept from a laboratory into a real product. But one thing I feel I don't like about being in a company is that really in a company setting, right? What happens is that in the entire company there is one single goal that is actually to commercialize your product and try to earn some money, right? And then your daily life becomes quite focused on one thing. It's just there are a lot of things you're trying to, I mean, optimize a certain device and trying to basically to balance the trade-off between what you can make and what you can design. And then it becomes a bit more boring. Then I decided, okay, that's probably not what I want. Then I decided, then I come back to the academia. And for us, there is actually another major choice we need to make at that time is whether we want to stay in the US or come back to China. Okay. And let's not talk about the politics for now, but there's of course some pros and cons here. And for many, I guess Chinese students still studying in the US still face the same thing. One of the major reasons is still we have this family issues here in China. All our families are still here, but in China, we find that over the last many years, okay, we really see the entire society is in this uprising trend. Okay, there are really things are changing day by day, and really feel really excited about all this. Okay, and that's really motivated us why we come back. Right? But there's also a trade-off. Okay, we found that when we were in the U.S., we were really have a quite nice work-life balance. Right? I mean, life is pretty happy when we were students or postdoc or working in a company. But I feel like after I come back, the entire work-life balancing becomes it's just totally gone, right? And I feel like to give some suggestion for our future students that I feel like really like nowadays the entire academia award is really competitive, right? So it's really a difficult road. And if you later on really decided to, if you want to keep staying in this road, then make sure it's really what you want, right? And just keep a positive mindset whenever you receive a rejection letter, whether for a job application, for a grant application, or for rejection letter for a paper, right? Just keep going and make sure that's really what you want.
Okay, it is interesting for you share your experience. You have a really diverse experience. Go almost different place and try different positions and you found something interesting. Professor Jagdish, you have so many students. When they going to have a job, graduate that, what's your opinion or your suggestion to them?
So what I tell Alice, thank you for that question. And then what I tell them is that, forget about your PhD topic which you worked on. Once if you have done your PhD, you've got analytical skills, problem solving skills, critical thinking skills, good writing skills, good presentation skills, and these skills you can apply anything in the world and whatever you choose. So please don't think that you're a meta optics person or a nanowire person or a solar cell person. That's all the detail. But those generic skills could be applied whether you want to go to government or industry or to academia. You have to choose whatever you feel passionate about. In the process, my students are working in all sorts of fields and they're all very happy with what you're doing. You have to be happy with what you choose and what you really enjoy what you do. In the process, you are having fun.
Okay, that's very, very good. Because I asked this question is these few days, I met some students. Yeah, they are PhD students, but they're working in different areas. So sometimes they are really scared to speak with me or communicate with me because when they see me, they say, "Oh, you are professor. You are much more serious. You want all the students to go to academic." Looks like that. So they say that I'm not in academia, I'm working somewhere, so maybe I should, go somewhere, not talk to you. But I tell them, okay, no, but you got PhD, not meaning you will go to academic, right? You can do a lot of things. That really depends on your own choice, on you know what you like. Like you said, Professor Jackie, I like that words. It really depends on you. That depends, on the professor. Professor now try to push you, go somewhere. No, your life is your life, right? Your career is your career. Yeah, that's very important. I see all these, two young professors give us a very good demonstration. So you can try a lot of things when you are young. So you have a capability, so you can do all these things well. So then just choose the best one you like, right? And you love it. That means you can get it done much better than anything else. You're not living for others, right? That's very good. How about another question is for these two young professors. So you go to the university after you get your PhD or a few years of a postdoc. How you set up your lab? Like Yuanmu, you go to China and go to a new university, and maybe you don't know anyone there, right? Yeah, you set up your lab. How you deal with that?
Yeah, thanks, Alex, for this nice question. And for me, one of the lucky things is that when I was a graduate student, I also joined a fresh new lab. Okay. My PhD advisor, Jason Valentine at Vanderbilt University, when I joined his lab, okay, he actually also just graduated from Berkeley with Professor Xiang Zhang. Okay, at that time he didn't even do any postdoc, and I actually that experience actually helped me a lot through the first couple of years here, right? So actually, basically, I learned a ton from my PhD advisor himself, okay, because I mean, how he succeeded or failed through different things. Okay, that can be very helpful. And also, I find that for my first few years here at Tsinghua, that I really feel like I have to be like a super postdoc in the first few years. Okay, have to do everything from scratch, and it's really also very important that you have to basically the first few students. Oftentimes people say that, like Alex, you also say that it's extremely important for the successful for the success of a research group, right? And I really have to spend a lot of time trying to mentor them all the way from scratch. And I found that maybe after 2 years now, they can already take over now, and they can start training some a newer generation. That's really makes my life much easier. Okay. And also, I found that one thing that since, as you mentioned, that when I joined Tsinghua, okay, I didn't know many people here. One thing important for new faculty members is that I feel like you have to be really resourceful, okay? Meaning that don't be afraid to ask for help, okay, either from your colleague or from many of the supporting staff in the university. Okay? Many times, if you are pushing out, okay, people are generally very nice to you. Okay? They will help you. It's not a good idea. Okay, you just try to just keep your question to yourself and just spend many days trying to figure out something simple. As if you can just ask someone and get an answer in a few seconds. And I guess that's what I.
That's very interesting. I think most of the Chinese, especially the young guys, they are really shy. They
Mhm.
do eager to ask questions, ask for help. Many times they are thinking, everything by themselves. That's not a good habit. You should learn from Yuanmu. Try to ask help. Try to get all the surrounding resources working for you. That's very important. Yeah. So, Michael, yeah, so you're from Harvard, you moved to medicine. That's also a big move, right? So, what's a challenge for you? Set up a new lab.
Well, certainly not as big as Yuanmu's move, but or not as far and not as different, but nevertheless, look. I completely agree with Yuanmu and with Alice that science is like a very social enterprise, and the more that you take advantage of these smart and excellent people around you, the better your life and your career will be, and the easier it will be to start new things and take advantage of opportunities. Definitely setting up a lab from scratch is very daunting. It's a very scary thing to walk into an empty room and then kind of imagine with no people and not knowing anybody really at the university, as Yuanmu pointed out, and imagine what that place will be, and take care of everything from kind of lab organization down to things like plumbing, but then also, of course, imagine all the scientific equipment and the personnel. But of course, that's also an exciting point, and that's why I took the job, and that's why people aspire for these kind of jobs, to be able to build something new. You always have the opportunity to build something, at least for maybe a narrow set of experiments. As if you're an experimentalist, you have a chance of building something better than what you had, let's say, as a postdoc or a PhD student, which is quite exciting. I think the biggest part of starting and building a lab and a lab group is really first recruiting, but then also building a lab culture, building a group
Yes.
culture. You really want the students and postdocs and yourself to be a cohesive team, to actively want to help each other and to be good at helping each other, to share in each other's successes and failures, so that there's a support system in place, and really make sure that everyone feels a responsibility for the lab, so that if something goes wrong, there's not like a top-down process where the advisor or the PI, tries to take care of something or tries to delegate, but really everybody wants to step up and fix issues as they arise and take advantage of opportunities as they arise. And so I really think that being thoughtful in how you build not only the physical space for an experimental lab, but also how you build your lab culture and your lab organization is very important. And I'm guessing we're going to talk about that a little bit more shortly.
Yes, yeah. Professor Jack Dish last week, remember, in the panel discussion. Yeah, we say that it's like a lab culture. Culture is like a family members everywhere. Yeah, you have a rich experience, but now I have really come to me one very interesting question is for you. Now, a top scientist, you almost can move the world, right? Yeah, everyone know you. You go everywhere, get big support, but back to 30 or some years ago, when you graduated from India and you go to another new country, so and then you set up your lab. What's the beginning? How hard it is. What kind of story you have? You can share with us.
So,
Yeah.
okay, thank you very much, Alice. And let me tell the particularly younger generation. I did my PhD in '85. So
Okay,
at that
18.
time, there was no internet and there were no computers,
Both
at
of
least
them
at that
never
time.
didn't born.
Born probably. Anyway, so in those days, we used to get magazines like Physics Today and IEEE Spectrum by sea mail 6 months late to India. I used to go to the library and note down all the advertisements in those things, and I used to apply for the positions which I thought are relevant to me. Over a 3 year period, I had more than 300 rejection letters. Okay?
God.
So then ultimately, I ended up getting a postdoctoral fellowship in Queen's University in Canada. And through a friend suggested me to apply to that group, but my field was semiconductors. I had to change my field, and I was working in Queen's University as a postdoc of developing magnetic techniques for detection of corrosion in oil and gas pipelines. So where is semiconducting thin films and where is detection of corrosion in oil and gas pipelines? Again, the same thing. We know how to do research, and you go to the new field, you learn those things, and you go and apply the same thing, skills you developed, you go and apply to those ones. So then another professor came to know that I'm a semiconductor guy working in magnetics. One day he came and asked me, Professor Jim Williams is starting a new department of electronic materials engineering at the ANU. Would you like to go to Australia? So that's how I came to Australia with a 2 month old baby and a 2 year contract to work at the ANU. So
Wow.
it's a brand new department. We had to build up everything from the scratch. It took a long time for us to be able to establish all the facilities which we needed. But that's where the determination, persistence, and perseverance. And you go one step forward, two steps backward, and you go one step forward. And those are all the normal process. Once if you're passionate about what you're doing, you don't mind the failures, you don't mind all the hurdles which you face. Ultimately, the determination to really achieve something is the one which will really drives you. And again, also particularly when you started as an academic, the students really make the difference. Good students, particularly at the early stages of your career, they can really make a big difference whether you're successful or not. I've been very fortunate. I had some wonderful students. That's how we built up the lab and created the culture which Mikhail has been mentioning. I always told people, first and foremost, be a good human being and then be a good scientist, not the other way around. It is important to be a good human being, and collaboration and cooperation is the way to go, not competition, and then is not the way to go, sort of thing. So creating that right culture is important, and I've been very fortunate. I have had a wonderful students and postdocs and young scientists work with me. I feel I'm grateful to all of them.
Exactly. Yeah. So how nice to show that stories. Yeah, that's really moved. And for managing the students, I think this two young faculty. Yeah. So when you try to recruit the students is one thing. When you see the students almost the same age, even someone was older than you, how you manage it? So, Michael, maybe you go first. You already have some rich experience here.
Sure, sure. Well, I've been a faculty member for 6 years, almost to the day. I think 6 years in a week, something like that. Definitely, it's a unique challenge to manage a group as an assistant professor, especially if you're coming either from a PhD or from a postdoc. One reason Alice already mentioned, right, that it's quite common to have students and postdocs that are close to you in age and close to you in the level of experience. But also, maybe more importantly, you have very little experience managing people, right? So when you're a PhD student or a postdoc, you're not really trained during that time, at least not formally in most places, to run a group and to manage people. And then all of a sudden, you're thrown into the situation when you have to do this and you have to do it well. And of course, a lot is at stake, right? Not just your career and your research success, which is important, but more importantly, you're all of a sudden responsible for the successes of all of the students and postdocs and everybody who works in your group, and that's a huge responsibility and something that you need to take very seriously. Um, I certainly can't say that I've figured out how to do this well. I think I've gotten better in 6 years, but certainly, I have a long way to go. But I have a few elements of an approach that I've slowly been thinking about this whole time that I think has helped. One of them is to be very transparent with the students and postdocs with my own tasks and my own challenges. So I think it's difficult to work for a principal investigator, to work with an advisor who doesn't share what's going on, and you then, as a student or a postdoc, you receive tasks, you don't know why you're doing it, you don't quite understand the process. And so I think explaining kind of not only the whole research process, but also kind of the grant enterprise, how funding works, how recruiting works, and then having the students and postdocs participate in that, maybe help you write some of these grants, help interview new incoming members, really helps build trust and build engagement, and then also helps everybody feel a responsibility for the group and to each other. And I think that's very valuable. Another element, I think, this one is going to be sound a little bit naive, but quite frankly, to work hard. I don't think anybody wants to work with an advisor who's lazy and to feel like the advisor is not pulling their own weight. And so I put in a lot of effort, and then quite frankly a lot of hours to try to make sure that I'm always giving back to the group and to all of the students everything I can to help ensure their success. And that means not only support their research, not only help with the papers and the conference talks and things like that, but also support their professional development. Make sure that when they're graduating and then departing the group, that they have all of the skills that will enable a wide variety of careers in industry and startups and academia, and so forth. That means work on and try to help improve writing skills and presentation skills and critical thinking skills, and of course science, and of course kind of collaboration and mentorship. Make sure that the group members, as they become more senior, have the opportunity to take on responsibilities and have the opportunity to take on mentorship roles. So if some of them do end up in leadership positions, either as group leaders or as professors, that they will have some of that experience going in. So I think kind of making it clear to all of the group members that you're bought into ensuring their future success, and then actually following through on that, I think has been really important for me, and I will continue to work to be a better advisor kind of along those axes in the future.
Okay, great. So Yuanmu.
All right, so I guess this is quite another important problem, right? So for me, I feel like I'm still also in the learning process of how to be a good advisor, right? So one of the problems there, as Mikhail earlier mentioned, that really none of us has actually received any formal training in terms of how to manage people, right? So that's really a big issue. Maybe I'll later try to suggest to our some of the university officials maybe. So, and Alex actually proposed, asked a very interesting question, like how do you manage students which is probably younger than me, or at the same age of me, right? So it's actually funny that I actually look back and I feel like I never actually had a situation that a student doesn't want to listen to me because I look too young or something. Actually, one of the major problem of I guess quite common in Chinese students is that they actually they listen to the professor too much. Actually, they're not too used to arguing with their
Challenging. Yeah.
advisor, asking questions. Right? That's actually the opposite side, I would say. Right? So on that front, I would say being a young professor actually could be a good thing. Right? That can promote, maybe sometimes they become less afraid of asking questions. So I guess that's a good part. And another way that I really feel like the way that we should convince our students is that not by our authority. They really have to try to convince people, to teach people with some proper reasoning. Yes, that's something for myself. I really want to keep in mind. Just don't try to push your ideas to your students just because you are the boss or something like that, right? And another thing I really fully agree with Mikhail that he talked about in his response to the last question, right, is that in order to basically to form a good like dynamics in the entire group or in between the students and the faculty members, is that really myself, I think that I need to be more considerate of each other, right? So we really need to know what we want after graduation. Maybe I mean, and also in terms of choosing like a particular research project, right? So there are things that they like and things that they don't like, right? Don't try to force it through. Just try to listen to what we want, and maybe that's a better way. And, overall, I mean, I feel like it's important for me just to every day walk into a lab or in the office, and I see my students, and we are both, I mean, happy when we see each other, right? And be friends or something. So, and that's quite important for me. I think one thing I really hate is that I'm not good at. I feel like me personally, I'm not good at doing like all this the interaction with people. That's something make me afraid or something. But still, I want to form a good dynamics with students, so we're happy staying.
Okay, it's interesting. I mean, for most young scientists or young professors have the same, almost the same problem because they never trained, how to deal with the people, how to communicate, and even, how to manage, different kind of peoples. But one more thing, very important for supervisor, for professor, is yourself must be a big demo for the group. Yeah, like why Professor Jagdish was so successful, can move in the whole world. It's because he's a big demo for his group, for all his students. Hardworking and collaboration and help everyone. That's very important. Professor Jagdish, yeah, I'm really admire and you in this. Yeah, you really done great job.
Alice. Thank
Yeah,
you.
exactly. Open mind to everything. So, yeah, today is pretty late for you. Yes, yeah. So after midnight is the early morning already. So yeah, I will get save a few minutes for you to go to bed, have a good sleep, and then we will go to Michael Hill's talk for his wonderful research. Okay, thank you all of you for this wonderful
Okay.
panel. Okay,
Okay.
thanks Yuanmu.
Thank you very much. Thank you
Yeah.
very much.
So
Very much.
now we move
Thank you,
into
everyone. It's great
the
to see you.